We mentioned before that when a light ray encounters a boundary between two media, it's going to do two things. Part of it's going to reflect, but part of it is going to enter that new medium. And so our topic of discussion today is what happens when that light ray actually enters the new medium. Now, light rays are going to speed up or slow down based in different media. Now, we talked before about how in a vacuum we know what the speed of light is and how that's the ultimate speed limit. It can't go any faster than that. But any other phase, any other thing that it travels through, it's going to go slower. And we also mentioned that light travels more slowly in solids than it does in a gas. It travels more slowly in a liquid than it does in a gas because there's more particles to get in the way, so kind of slow things down, so to speak. So when a substance causes the speed of that light wave to change, the light wave is going to bend. And I, again, kind of mentioned before in one of my other videos that you can think of it almost like a marching band. And if you have a nice straight marching line in a marching band and they're marching across a football field and part of the marching band hits a mud puddle where the mud is super sticky and deep, that piece of the line is going to slow down because their feet are stuck in the mud. And so the other part of the line is going to keep going at the same speed, but the part where they got stuck in the mud, they're going to slow down, and so the whole line is going to bend. Now, that's not a perfect example, but it does kind of give you an idea that when you enter a new medium, the light ray is going to slow down. And so we're going to look at an example of that here. I've got a container of water, and this is supposed to be a flashlight, and it's shining a light towards the beaker of water, towards a container of water. And so right at the point where the ray hits the container, you can probably see that black dotted line. I drew my normal in there. And so part of that is going to reflect just like we talked about before. And so the angle of incidence is going to be equal to the angle of reflection on the outside. But what's going to happen once it goes in here? Well, if it would keep going along the same path, it would look like that. But once this light ray hits the water, it's actually going to slow down. And so when it slows down, it's going to bend and it's going to go this way instead. Because whenever light refracts into a substance where it slows down, the light ray bends toward a line perpendicular to the substance it strikes. Okay? So the light then is going to be on this path as it goes through, and it's going to continue straight through until it gets to the next boundary, which is going to be the other side of the container. So once again, if I constructed my perpendicular right there, the point where it hits, it's gonna bounce again. So part of it's going to be reflected, but part of it is going to go on through the glass. Now, if it would go straight, if I could actually draw a straight line, if it would go straight, it would go right there. But remember, we're going from water back into air, and this light ray travels faster in the air than it did here. So once it's traveling faster in the air, it's actually going to bend again. And this time, because it's speeding up, it's going to bend further away from that perpendicular. Because if the light ray speeds up, it's going to bend away from the perpendicular. Okay? If you need to pause the video to jot down this diagram or to jot down any of these statements, you may want to do that. I think there is a similar diagram in your book, but just in case there's not, if you like that one better, if you want to write it down yourself to help you remember it, you may want to do that. Refraction is also one of the reasons why we see a mirage on a hot day. If you have ever been driving on a hot day and you look way down the road in front of you, it sometimes looks like there's a pool of water across the road. But when you get there, it's not actually there. Well, what happens is that right above the surface of the road, the air is really, really hot. And so the light is going to get so far down and it's going to start refracting. And so some of that refracted light comes back and bounces into your eyes, but it gets refracted before it ever gets to the surface of the road. And so what you're actually seeing is a reflection of the sky that's actually higher than where the surface of the road is. And so your brain looks at that and says, well, the road should be here, but the light's reflecting from here, so therefore it must be covered with water. And so that's why your brain thinks that you see water when there really isn't any water there. And that's true. I mean, you've seen probably cartoons, or you've seen stories of people in the desert where they think they see water and it really isn't there at all. So that's why it happens. It all has to do with refraction of light. Now, we also can use, just like we used reflection of light to do cool things with mirrors, we can also use the refraction of light to do cool things to help people like me and maybe like you who can't see very well if we don't have some help with either contact lenses or glasses. So let me see if I can give you an idea here of what actually happens in a situation like that. So your eyeball obviously sits back in your head and is round, and so you have your pupil here at the very front is what lets in the light. Right behind your pupil is the lens of your eye. And so the lens is going to take the light rays that come in and it's going to bend it and focus it in different places. And this piece back here is called the retina. And so that's where your the eye is supposed to focus all the images of what you're seeing on your retina, so then your optic nerve, which comes off from back here, can take those signals to your brain, and your brain can interpret what it is you're seeing. So when things come in, they should be coming in and they should be focusing at a certain point back here. But sometimes what happens is that these lenses kind of get malformed, or as you age, they don't work as well as they should. And so sometimes the light rays, I'll do it in a different color so you can tell, sometimes the light rays may come in and they may focus up here, or they may come in and they may actually want to try to focus back here. And if that's the case, then your brain can't figure out what you're seeing because it's getting a very blurry image. So in that case, what we do is we use one of two different types of lenses to focus the light in a different spot so that you can see it. So there are two types of lenses that you can use. One lens looks like that and is called a converging lens. And the cool thing about a converging lens is that when the light comes into it like this, it all is going to get bent, and it's actually going to bend at this surface and it's going to bend again at this surface. I'm not going to do a whole lot of that bending just because I'm trying to get the general idea here. But this is actually all going to get bent, and then this is going to focus it all in a point back here. So what happens then is if you're focusing in the wrong place, then you put this kind of lens in front of your eye, and it will help to focus, it will work with the lens of your eye to get that light ray focused back on your retina where it's supposed to. We also have a type of lens like this, which is called a diverging lens. And when light hits a diverging lens, it does exactly the opposite. It comes in all parallel, just like it did before, but then as it comes in, it actually starts to scatter like this, and it bends everything away from it. And you may be going, well, how does that help? Because what happens is that, again, depending on whether you're focusing too close, too far in front of the retina or too far behind the retina, one place you're going to need this type of lens, and the other place you're going to need this type of lens, because these lenses work with the lens of your eye to shift that focal point back to your retina again, okay? Because here you're bending light rays away from each other, and here you're bending the light rays toward each other. So both converging and diverging lenses are used to correct vision, and it's all a matter of refraction of light.